Okay, so what is this saying? Well, I think it's important that you guys get to the point where you can read a math book, because a lot of high school students get to calculus and they've never really sat down and read their books. Calculus is one of those books you just can't rely entirely on your teacher notes, you know? So you should try to read it. So let's just read through this theorem together carefully. There are two conditions and one conclusion on this theorem, right? The first thing is f is differentiable at every point in an interval. The second is that f prime is never 0 in that interval. Both of those are really important. If you don't satisfy the two premises of a theorem, then the end conclusion of that theorem is not valid, right? So you have to satisfy the two initial parts of the sentence before you're allowed to apply the rest of it. This will be really important when we get to the mean value theorem. That thing has rules. You can't just use that thing on every problem, okay? Once you've established that the first two underlying things are true, you may continue to read on and make conclusions. If even one of those original premises is not met, you cannot conclude the words after then. So the stuff afterwards is meaningless. So in a conditional is not valid unless you meet the hypothesis part of the sentence. Very important. Okay, so I have to try to draw a graph that is differentiable at every point, and at the same time, f prime is never 0. Okay, so everyone do that on your paper right now. I want to see a graph on your paper that is differentiable at every point. Why don't we just say that the interval is from 0 to 10? Why not? Let's just let the interval be from 0 to 10. I want a graph that's differentiable, and I want it to never be 0 in that interval. F prime, I mean. Never to be 0. Okay? So everybody's drawing right now. Okay, so what do we have to draw? Something with no corners, no cusps, no vertical tangents, no breaks, and no horizontal tangents, according to that second given. Right? Okay, so that kind of limits what we can draw. How about something that's strictly rising? Anything that's strictly rising. So it could be like e to the x. You maybe drew a straight line. But from 0 to 10, the graph is completely on the rise. No corners, no cusps, no vertical tangents. Okay, you could draw that one. You could draw this one. Nothing wrong with that green one. What would not be okay is to draw this. This one in blue, I can't have. Why? Although it is differentiable, it has a horizontal tangent right here, see? And that was forbidden when it said f prime is never 0. Okay. So, something completely rising. Or something that's falling, right? So you could also draw something like this. Nothing against drawing it going down. So I noticed some of you did this. You drew a graph that goes down. Many of you just drew a straight line. So you could draw that. You could draw something like this. This is a cool function. Just got to be careful not to have any horizontal tangents on there. So even these spots that look like flat spots have to have a negative slope. No 0 slopes anywhere. Okay? Now that we've drawn some examples, let's continue reading the sentence. What is it saying? It's saying that f has an inverse. F has an inverse. I thought the rule for inverses was that f had to be 1 to 1. Do you guys remember that phrase from your pre-calc days? If a function is 1 to 1, then it has an inverse. Raise your hand if you remember that phrase, 1 to 1. Okay? Can someone tell us in their own words what it means? What does it mean for a function to be 1 to 1? For every x, there's one y value. That's the definition of a function. What is a 1 to 1 function? Yes. For every x value, there is one y value, and for every y value, there's one x value. that means that if a function is only one-to-one if it passes the vertical line test and the horizontal line test. Okay? So that is true for my red one over here. It passes the vertical line test. It passes the horizontal line test. It's true for the green one as well. It's also true in this picture. You can draw horizontal lines or vertical lines, and they all touch the graphs at most once. Okay? So last year you learned it as if there is a one-to-one function, then it has an inverse. Okay? All right. What is the second part saying? And f inverse is differentiable. F inverse is differentiable. What does that mean? It means there are no sharp turns, no vertical tangents, no breaks in the inverse graph, and so forth. All right, so let's go on to the next page here. We've written the theorem. Here's an example of this. Does anyone recognize these two functions? This is f of x, and this is f inverse of x here. Does anyone recognize these? Anyone care to guess which functions I'm using? Yes, this is e to the x. What is the inverse of e to the x? ln of x. That's right. Good. Okay, remember, if y is e to the x and you try to solve for the inverse, you're supposed to switch x and y around, right? So it's x equals e to the y. And then we had trouble isolating y, so we invented the ln symbol. The log was invented for the sake of isolating y here. Okay? That's one way to think about it. So these are inverse functions, as we know. Remember the symmetry? The symmetry is that they are a reflection of one another over the y equals x line. Let me draw that a little bit better. They are a reflection over the y equals x line. This thing. This line is super important. Okay? Make that thing dashed. That didn't work. You shall henceforth be dashed. Obey. There you go. That's the y equals x line. So, what are we saying? We're saying, listen, if the first graph, let's say that's e to the x, if that graph has no corners, no cusps, no vertical tangents, when you switch x and y, we could then say that ln x has no corners, no cusps, and no horizontal tangents. Okay? If we further require the graph on the left to have no horizontal tangents, we can then be sure that the inverse has no vertical tangents. Okay, so this is very, very important. Listen again. I'll say it again. If the first graph has no sharp turns or bends in the graph, no breaks, the reflection obviously won't either. If this graph has no vertical tangents, in other words, differentiable, then the inverse graph will have no horizontal tangents. Remember, x and y trade places. But that doesn't mean much. Who cares if it's horizontal tangents? But if this graph has no horizontal tangents, then this graph will have no vertical tangents, and we have full differentiability. Okay? Okay, it's really important to understand the last tiny bit of this sentence, right here. The inverse will be differentiable in the interval f of I. What is that talking about? What is that talking about? So let me do my best to explain that to you so you really understand the whole theorem. We said that we wanted our graph to be differentiable from 0 to 10. Many of you drew something like this. Okay? Remember, this is the point 0, f of 0, this first one. So this is at a y value of f of 0. And out here at 10, the y value is f of 10. When we do the inverse function, it reflects over the y equals x line, right? And ends up over here. It's not a very good drawing, but something like that maybe. Now this is f of 0, and this is f of 10 over here. The domain and range switch, see? And this is 0 and 10 now. The y values are the 0 to 10. So we are saying that the inverse graph is differentiable over f of 0 to f of 10. And I forgot my parentheses there. Okay, so that's what that last part means. The interval has changed because we flipped it over. The y's became x's. X's became y's. So domain became range, range became domain. All right, so hopefully now you can read this sentence in the book and you'll be like, oh, okay, we've got two criteria, but if we draw that type of function, we know there's an inverse. We know it's differentiable on that interval. All right. There's one more thing you need to know. If e to the x is reflected and has no corners, no cusps, no horizontal tangents, and no vertical tangents, we get a very nice inverse graph. It is a function. It is differentiable. Okay? There's one more thing you need to know. If it's differentiable, we should be able to find the slopes. Right? Okay, so let's talk about one or two of these points on here. Why don't we talk about this point right here? What are the coordinates of that point? 0, 1. When reflected over the y equals x line, that point lands right here. What are the coordinates? 1, 0. If I had you draw a tangent line right here, what do you suppose the slope is?
1.
Sure looks like 1. We'll show on Friday that it is 1. What happens if you reflect that over and land at the point 1, 0? What is the slope here? Okay. Let's go now and talk about this point up here. This is the point 1, comma, e. When I reflect that over the y equals x line, where does it end up? At e, comma 1. Good. What do you think the slope is of this green line? Maybe 1/3. I'm sorry, maybe 3 over 1. It's a little steeper, right? You guys with me?
Yeah.
This is really important. It turns out that the slope of that line is e. Any idea what the slope of this line would be? 1 over e. Why? It has to be the reciprocal because remember, when x and y trade roles, rise and run trade roles. Right? So slope becomes run over rise, you know, and so we have a new relationship here. The derivative on an inverse graph is just the reciprocal of the old point. Not an opposite reciprocal. These green lines are not perpendicular, but just regular reciprocal. So if that was slope 3/2, this would be 2/3. All right, now we're ready to actually do a problem. Okay, so imagine you were given this problem back in pre-calc, and the teacher said, okay, we're going to talk about inverse functions. This problem would be way over your head, because your teacher would probably say, all right, let's all find the inverse function. How do you do that? You switch x and y. Okay, that's right. So you do x equals y to the 5th plus 6y plus 8. We got a problem. The next phase is to isolate y, and that is not happening. We cannot do that. But what is, yeah, we now know. We saw the same problem yesterday, or 2 days ago. We had a function, or a relation, we could not isolate y, remember? So we talked about how you could take the derivative anyway. Does that have anything to do with what we're talking about? Well, listen, we are not being asked to find the inverse function. This is a dead-end road for most people. I'll bet Wolfram Alpha could do it. Besides, how do we even know there is an inverse? You know, how do we even know it's a function? Maybe we're wasting our time, and a lot of time, trying to get y by itself. Well, we can guarantee that there's an inverse. Whether or not we can find it, we know there's an inverse. Look at instructions for 1. What does it say? Find f prime. That's easy. What's the derivative? 5x to the 4th plus 6. Okay, what does that have? Anything to do with inverses? Why? Who cares? Who cares if you can find the derivative? Like, how does that help you with inverses? Totally different topic, right? But listen, someone give me a number.
42.
Okay, it's a little big. I was going to do the 4th power. 2? So if you plug in 2, you get 86. Give me another number. Negative what?
1.
Negative 1. That's going to come out to 11. Right? If I plug in 2, I'm going to get 86. If I plug in negative 2, I'm going to get 86. If I plug in 1, I'm going to get 11. If I plug in negative 1, I'm going to get 11. What kinds of answers will this always yield? Positive. Right. I can plug in 0. Still going to give me 6. You can see that the slope of all points on f is positive. It doesn't matter what x you give me. F prime is going to be positive. That means that f is always on the rise. It's always rising. The derivative is always positive. All right, so that's the clue here. It says, use this result to show that f has an inverse. This is your f prime of x. Since f prime of x is positive for all x's, there's no exceptions. You can plug in anything you want. It's always something 6 or larger. Since f prime is positive for all x, f of x, that's this graph up here that I don't even know what it looks like, is increasing for all x. See, if the derivative is always positive, the graph never stops rising. So I don't know what f looks like exactly, and I certainly don't know what its inverse is, but I know this. It definitely passes through the point 0.8. I can tell by looking at this problem. It definitely passes through the point 115, and it's always on the rise. Okay, so this is my rough sketch for this graph. It passes through the point 0.8. It passes through the point 115. And it's always on the rise. You guys with me? Okay. So since f prime of x is positive for all x, f is increasing for all of x, that means that f is therefore 1-to-1 and has an inverse. If it's rising, 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 it will pass the horizontal line test. Okay, question?
Yeah, you said 1-to-1 means that for every x there's 1 y, and for every y there's 1 x.
That's correct.
So if you plug in like 2 and negative 2, you get the same thing, right?
Into the derivative.
Oh, you're talking about the original one?
The original function has to be 1-to-1 in order for the function to have an inverse.
Okay, I thought you were saying the derivative was 1.
No, the derivative is an even function,
Okay.
which means that regardless of what x's you plug in, you get the same output behavior. So what that means for the original graph is that that thing is always rising. Always rising. And if it's always rising, then when you try to draw horizontal lines like this, it should pass the test. Okay, so pretty profound how we use the derivative to help us understand the inverse function. It does exist. Okay, now let's go on and talk about whether we think the inverse function is differentiable. Okay? Okay, so if we're going to make statements on the AP exam, let's stick to the definitions in the book. Okay? According to this rule over here, the inverse will be differentiable under two conditions. One, we have to require that f is differentiable at every point in the interval. And since they're talking about all real numbers, we have to argue in our little paragraph that f is differentiable for all x. We also have to argue that f prime is never 0 for all x. Then we will be done with that part of the problem. Okay, so f inverse will be differentiable if f is differentiable and has no horizontal tangents. I believe both of these are satisfied because f is differentiable, is a polynomial, right? F is a polynomial. F is a polynomial function. And therefore has no corners, no cusps, no discontinuities, and no vertical tangents. Since we showed that f prime, the derivative, is positive for all x, f has no horizontal tangents either. So my conclusion is f inverse has no corners, no cusps, no discontinuities, and no vertical tangents. Why am I saying f inverse has no vertical tangents? Because f had no horizontal tangents. Therefore, f inverse is differentiable for all x. I know that's a long paragraph, and you could have simplified some of it. For example, this sentence up above about a polynomial function has no corners, cusps, discontinuities, no vertical tangents. You could have just stated that as a polynomial function is differentiable for all x. Okay, so you could simplify that. But I'm trying to teach you what this all means. So when you read through this again later, you'll be like, oh, I see. Or maybe you'll be like, what? In which case, you just ask me again. Or watch the video again. All right. We need to answer part C. Okay, part C. So part C gets more concrete, and it's just basically saying to find f inverse of 15 and f inverse prime of 15. Okay, so it's a two-part question there. Erasing all this. Okay, remember I actually already made my rough sketch of f. Let me draw it again. I said I don't know exactly what f looks like. I know it's like a fifth order or fifth degree polynomial, so it goes up on the right and down on the left, you know? Like there's an arrowhead there, there's an arrowhead up here. From the derivative, we made an argument that this thing is always rising. So it could have up to 4 turning points, but it turns out it doesn't have any. So this thing is just strictly rising. We said it passed through the points 0, 8, and 115. So let me plot those again. This was 0, 8, and this, let's say, is 115. So this is kind of my rough sketch of the function. Close enough. I would like to talk about the inverse function. Okay, so the inverse function would be a reflection over this line, right? Right here. And my polynomial graph is not that great. I'm just trying to glean a little bit of information about my inverse from this guy. Can you tell me a couple points that would be on the inverse function? 8, 0 and 15, 1, right? 8, 0 is on there. 15, 1 is on there. They have to be, right? And maybe the graph looks something like this. This isn't even that accurate anyway, so I don't know why I'm bothering to connect the dots. But we're really close to answering the question. The first question was asking, what is f inverse of 15? That just means when x is 15, and you're on the green graph, what's the y value? So what's the answer to that? 1, right. So f inverse of 15 is simply 1. Okay. The second question is asking for what is the inverse's derivative at 15? Well, listen, you don't have the inverse function, and you certainly can't take the derivative of something you don't have. But maybe we can just steal the slope of this red line. We'll just take this slope and do a reciprocal, because that has to be the slope here anyway. See? We're trying to find the equation, or the slope of this line down here. And we won't be able to do it with an explicit function, but we can cheat and go back and find f prime of 1, because that will be the inverse's derivative at 15 if we do a reciprocal. Okay, so what we're seeing is that we can cheat and get the inverse's derivative at 15 by simply doing 1 over the original's derivative at 1. And remember, the derivative was 5x to the 4th plus 6. So the answer is f inverse prime of 15 is 1/11. What we're saying is this red line at the top has slope 11, and the red line at the bottom has slope 1/11. So we're kind of cheating the system. We do not have f inverse, but we analyzed f inverse by staring at f and its derivative. Okay, that's all we have time for. I have more examples tomorrow that involve trigonometry stuff. So if you're going to miss tomorrow, the video is really important. It tells you how to take the derivative of arc sine, arc cotan, arc tan, arc secant, all that stuff. And they are the hardest derivatives of the year. So memory.